Okay, so today I think we'll just go back over a few things that we've been doing. So sort of to draw a line under the work we did in the ICFAS 2024 conference. In that, I had a sort of a presentation, and we were attempting to, define the dimensions of the hypersphere using different models like the support vector machine model and a four-dimensional wireframe sphere. But then there was also an attempt that I kind of, during the presentation, I thought it was still correct, but then afterwards I kind of recapitulated it and refactored it a bit and realized that there were some steps missing. So that I mentioned that in the last presentation we did, and then so I was able to go back and discover what went wrong, and so hopefully I can share that and share the correction with you guys. So start. Yes. So we have this data frame, and it's got the object ID of the galaxies, obviously, the right ascension, declination, and this factor here, which is some incidence factor. Then we have the G, the Z redshifts, then the XYZ components. So these are just the Cartesian coordinates of these values here, and then and then we have the polar coordinates as well. So all this data is from Sloan Digital Sky Survey as well. So you can get that from this Sky Server, I think it's called. Okay, so to start with, we drop duplicates and we just sort the values. So this is meant to put all the galaxies in order, like in terms of redshift, Z redshift. So basically, we just have a straight line of galaxies going out. So that the order or the magnitude of the redshift increases the further they are away from us is the concept. Okay, so here we just have a it's more of a test run. Okay, so I'll just get into the main point of it. So this is a bit of a linear regression model, which is interesting that it has a slope that's not equal to 1, which had been the case previously. Then we can create the recessional velocities using is it the Lorentz equation or Lorentz transform? Either way, it's all based on what's that? The Doppler shift, which I believe was invented by Vladimir Voigt, I think his name is. So that's that anyway. So there's the recessional velocity distances. So this is according to the Hubble constant or parameter, which means that this line has an angle of around. Well, we're using the logarithm of 2, the natural logarithm, but you could use, so it's around 69.314. But we could use like I think the current estimate for the Hubble parameter is somewhere between 68 and 72, and the differences come from different types of measurements. Some of them that use the cosmic microwave background or the tip of the red branch, the kind of distance ladder model. And as these two, as those methods have been refining, they found that the values, rather than converging, have been diverging, which is, referred to as some sort of crisis. Although some astronomers obviously don't like the word crisis, crisis of cosmology. But okay, so just create a copy of the original data frame here. So this is a little bit messy because it's a work in progress, or it was a work in progress. So I'm not entirely sure which one I'm supposed to run here. I'm not really as prepared as I should be for this. I know that I did the work there the other day and I got the results. So so effectively what we're going to do in this function is we take the Cartesian coordinates and we modify them by the distance. So maybe this is the one. Let's try running that. Although that looks like it's only, let's try running this one then. Oh. Okay, that looks good in a sense. Yes, I believe that's correct. Yeah, that looks right. So yeah, we have the XYZ Cartesian coordinates for the galaxies. Then we map that to the hypersphere and then multiply by the distance that we want. So essentially we're saying, okay, the hypersphere is going to expand by however much dist is. And then we reproject it back onto the tangent plane. And then we have our projective point as positive distance in the fourth dimension. We calculate our hypotenuse value using the norm 2 value. And then we want to subtract all the other edges from the hypotenuse to get the distance value to each of the galaxies in our data set. And then we once again apply the Doppler shift equation using speed of light and our natural logarithm of 2, and that should give us our distances. So, but what we find is when we graph it, then we find that the slope of this line is exactly the same as our original slope, and this is the case, I believe, no matter what value we put in here. So if I just run this again. Yeah, so essentially this tells us absolutely nothing because we can alter the size of the hypersphere all day long and we will always get the exact same answer. And the reason for this is pretty obvious. It's because we've used this natural logarithm of 2 for the slope for the projected galaxies, and we've also used it for the conventional distances here. So if I said that this slope was 70 or something, I'm wrong. This was just whatever Hubble parameter we selected at the beginning, which was the natural logarithm of 2. So the fact that we've used the exact same value in both instances, we get the exact same results, and that is the that I believe is it. Although looking at it now, I'm seeing that this line extends to here, whereas this line extends up to here. So perhaps if we were to, let's alter it and see if that makes a difference again. Because maybe if the distances become more, okay, I should check this. I think so, 39.8 billion in the x-axis and 9.22. That should remain the same. So I'm guessing no matter what value we put in here, we get the same results as well. If you can remember those numbers. Yeah, I think they're the same numbers, aren't they,
Yeah, it
Rajan?
looks about the same. Looks about the
Yeah.
same.
So ultimately, I mean, are they about the
So,
same or are they exactly the same? Well, I suppose it doesn't,
I
we don't
didn't
know
check.
because we don't have absolute precision, but I
Okay.
I don't think there's any change there. I'll just run it
Yeah.
again.
I didn't see anything.
Yeah, I didn't see any change either. So, well, we'd expect quite a large change. So there's no way to match these two things, I don't think. So that's really it from that perspective. So that's kind of good news because it's a null result. It tells us that this method doesn't work and it's not going to tell us anything. So the next step then is to shift into the next phase for this project would be to shift into a different mode that just measures the distances of the hypersphere in relation to the z redshift parameter. Now, how do we do that? Well, we need to I need to install Mathematica, and for that I need to use a different computer because this one's the software is kind of out of date, and I need to also like buy Mathematica, essentially rent it or whatever. So that might be. But the good thing about that is, the precision is way higher. So I've tried MATLAB and stuff. They're supposed to have floating point values of 128, but apparently they don't have it in the new versions. They do have certain methods to calculate large numbers to high precision, but the methods are a bit archaic. I think they're all working with hexadecimals, and it's not very clear what's going on. So, yeah, it's not very user friendly, I wouldn't say, and I'm not even sure if it'll do what I'm looking for anyway. So, what I'm looking to do, just to get to the point, would be we need to calculate the distances of the galaxies, which would be in like tens to hundreds of trillions of kilometers, and we need to do that down to the precision or accuracy of the wavelength of a hydrogen element. So obviously we can't do that with Python because it's very just doesn't have that capability. So that'll be the next thing.
Can you use Wolfram? You cannot use Wolfram, right?
Oh, that's what I mean by Mathematica. Yeah, Wolfram Mathematica. Yeah.
Okay.
Okay, so
you have to use another package. Okay, another package you have to use.
Well, another programming language altogether.
Yeah. What will be that?
What do you mean?
What would be the new programming language?
Oh, it's called Mathematica.
Oh.
Yeah, Wolfram Mathematica is its own programming language.
Oh.
Yeah.
Yeah.
Okay, so
but will it work in your case?
This is what I don't know. So I'm hoping, like I've gone onto Wolfram Alpha, I think it's called, which is the online notebook. So you can interact with it. It's very, very useful, obviously. I'm sure you use it quite a bit, but yeah, it's great. I went on there and I just did like a small calculation, like minus the wavelength of a hydrogen element from a really large value with, I think it was 21 zeros or something like that, after the main number or whatever. So, and it worked. It gave me an answer. So if I can get the same results out of Wolfram Mathematica, then yeah, no problem. Well, it's going to be tricky. It's going to take a while, but I think I'm probably going to put that on the back burner for a while. So there are other, there is some other research that I've been working on recently that, Just trying to remember where it is, though. I was just working on it last night, and so it should be here, but I don't see it. If I could remember what it referred to. It's to do with particles in the 24 cell. Okay. So there's this as well that we were talking about before. So can you do import pretty print or something as pp? No. Import pretty print. Oh yeah, okay. And then that's how we call it. Yeah, okay. So pp pprint, I mean, and then let's go with that. So the idea here was to recreate the trigrams of the I Ching. You'll recall, excuse me, before that we were looking at the I Ching in relation to Terence McKenna's Time Wave Zero. So the I Ching is a system of, it's a system of Chinese divination that was basically invented by, so it's related to magic squares, and it was invented by some important guy. I think it was a king or something, who saw this turtle climb out of the Yellow River. Was it the Yangtze River or something? And it had these dots on it. So it had, like, on its shell, it had 9 sort of segments or quadrants, and in each quadrant was a dot, or a number of dots. And if you added them up, didn't matter which direction or diagonals or, columns or rows, they all sum to the same number. So this kind of became the basis of the I Ching and the trigrams, because there was I believe there's 8 trigrams. So, and there's 8 numbers in the magic square, aside from the central one, which never changes. So let's say I believe they used a system of divination where they had these things called yarrow sticks, and the different yarrow sticks would have different numbers of like you know when you have a stem, and then the stem has like a nodule on it. So the yarrow sticks would either have like an even or an odd number of nodules, and then I think they would just hold them together in like a column, and then some of them would fall out or something, and those were the ones. But you could also use a much simpler method is to use 3 coins. So you get when you throw it the first time, you get heads, 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 or tails, tails, heads, and so on. And so that builds up this kind of binary sequence. And so those are the trigrams. And then we have like this along the top, and then the same thing again here to create like a Cartesian product where we just concatenate the values, and that gives us the hexagrams. So, and then that'll be 64 hexagrams. And then, so based on which hexagram you got, you then look up a book and find the number. So there's a sequence called the King Wen sequence, which is this system of numbers here. So we reordered the hexagrams in terms of this sequence. So we can go ahead and kind of do that. And there we go. So there's the sequence. There's the hexagrams associated with that sequence. Now, it's been a while since I looked at this, so I might be a bit rusty on the details. But you'll recall from previous TEGS kind of live coding sessions and discussion sessions that we've had that we've been looking into things like hypercharge and spins and things like such of that nature with particles. And you were looking into, I believe it was group theory with a matrix that wound up being 8 by 8. And so the idea was to have like a row vector that you would multiply. And I think you were also bringing in kind of Einstein curvatures and stuff like that. So it's interesting. You know, so I remember when I saw that, I was thinking of this because I'd done this work previously. I was meant to email it on to you, but then my computer crashed and I lost a lot of notes, so I wasn't able to do it. So instead, I recreated it here. These are just the King-Wen sequence then in order with the new numbers. Okay, so what are we doing here? I for I. We take a copy. Okay, I think that I'm not sure what that is. Forgotten, but hopefully this will become more clear as we go along. Oh yeah, so I think we're inverting the sequence here, and then why are we doing that? Yeah, like I said, it'll become more clear as we go along. I think this is the comparison between the King-Wen and the normal sequence. Now, oh no. Yeah, so you see that this is just, this column here is just this column shifted back 1. So this second row here becomes the first row. Third row becomes the second row, and so on. So all the ones at the beginning go to the end. And then we just subtract, or no, we don't subtract. We kind of, you know, looking for the differences, like how many times does this, if this is the hexagram, and then this is the next hexagram, which is just, you know, the next one up. And then we ask, well, how many times did the heads and tails change? So here, all of them have changed, but here only 2 of them have changed. So the difference here will be 6. The difference here will be 2. And again, the difference here will be 4 because all of those have been rearranged. Okay, so when we do that, we get the differentials in a list. And as you can see, this is based on work now by Terence McKenna. He was the first to do this. So the one observation he made early on was, okay, so the maximum number is 6, and the minimum is 1, but there's no number 5 difference. And the interesting thing about that is the same property also occurs in hypercharges for the standard model. So you can have I believe it's hypercharge. You can have a hypercharge of 1 or 6, but not, you know, in between those numbers, but not 5. So I thought that was an interesting sort of characteristics. So here's the charges for the fermions, left and right, and matter and antimatter. So we can list those with their respective charges. You know, so obviously the electron has charge 1. The neutrinos have charge 0 because they don't have electric charge. They work off the weak force. Then the quarks have like either they have fractional charges, or we can multiply these so that, you know, at the end of the day, the electron has charge 3, which is actually probably the correct thing to do. Okay, so now we have the charges, and then this value, I believe, is used in the creation of the hypercharges. So, right, oh yeah, no, so this is just the charges multiplied by 3, which is what I was saying. So we get rid of the fractional charges. Then we move on to weak isospin, which is used in the production of hypercharges, I believe. So we do that. It's just a kind of a simple formula. And now we create the hypercharge, which is just the charges minus the weak isospin. And there you see, we have all the values from 1 to 6, but not 5. Okay, and this is just them grouped, you know, in sets, which ones correspond to which hypercharge value. So differentials I, looks like we're kind of reordering things. Oh yeah, so these would be like, these are all of the particles that we're looking at. Now, obviously, this is just electrons down, up, and okay, for some reason the neutrinos aren't there, but you know, we could change this out to a mu particle, and this could be changed then to a strange. This would go to a charm. So we're just moving up the families, but it's sufficient at this point to just look at current. Oh, wait a second. Oh, it looks like we've run into a problem. Where's differentials? Maybe I forgot to run something, or I may have moved the. Maybe I did forget to run that. Okay, let's try again. Okay, so this is just saying. I think this is just an extended list of the previous ones. So, or would this be? Ah, okay. And yeah, and then so this is obviously tying it to the hexagrams that we spoke of. This will be doing it in relation. This same thing, but King-Wen sequence this time. And no, I don't think that's important. It might be important for later things. So what we wanted to do was print that. Okay, so here it is, the 8x8 matrix of the particles tied to the differentials by their hypercharge. And we just, so this is the kind of sequence we get. But you know, there's other ways of doing it, because as we noted,
what is this DXR? What is that? DA?
Oh yeah, that's a good question. So down, and then the star stands for anti. So this is the anti-down particle, and then or is just right-handed spin. So that's the anti-down right-handed.
No left-handed, right?
What?
No left-handed particles, right?
No, there are particles. We've got electron left-handed, but there's no anti-left-handed electrons in this situation, and there's no. Oh well, maybe there are, because I'm seeing that there are anti-right-handed particles and normal right-handed particles. So we're not dividing it in terms of like weak and strong, you know, the weak symmetry breaking rules. I don't think we are, but I'm a bit confused why there's no anti-left-handed particles.
I thought some of them are forbidden, right? Some of the left-hand particles don't exist, right?
Oh, that could be true, yeah, with the with the neutrinos.
Mm-hmm.
Okay, we do have anti-left for some reason, but we don't know. We don't know about if there's no you know, about the forbidden neutrinos. It's either that A, we haven't detected them yet, or B, they don't exist.
Mm-hmm.
So yeah, so I just leave them in, you know, because there's a symmetric kind of element to having them in. But as we can see, there are no anti-left particles, I don't think, which is a bit odd. I mean, another odd thing is we have like this string of left-handed electrons here in a line. But really, other than that, I wasn't able to discern any pattern here, or really spend any more time kind of. Oh wow, that's not right. Oh, something wrong happened there. See, the problem is to know where this process starts. Like, I suppose it could start here. Go back and we just run all of those. Let's try not pretty printing that. Still the same problem. Oh, this could perpetuate down through all of the things until I figure out what it is. So rather than running them, we'll just look at the outputs as they are. Unless I run it from the beginning, of course. So anyway, you can see I don't think there's, and here it is with the switching out the lighter elements for the heavier elements, I think. Although I'm noticing this electron neutrino probably shouldn't be there. I don't know why that's there. Yeah, so that's it. So it was more just a fun thing to try and do, but I don't think you know, really, yeah, it didn't really amount to much. I don't know if going back to your own research with the group theory. Oh, that's interesting. Why is hypercharge I not? Oh, that probably needs to be an int value, maybe. Or there is no. Ah, okay. Huh. And I'll have to look into that. I'm not sure where that error came from. So yeah, but you might be you know, I don't know how much use that is from the perspective of your own research to have a matrix such as this. Yeah.
Yeah, I've come to a situation where we start adding, you know, the time aspect. So I worked on that, and there is a new paper I sent out now. I mean, there is another paper I told during the ICFAS conference, and that paper is almost ready. It should be, you know, the final, you know, some editing, because I had gone through few editing, because each time they correct something, but mostly it is corrected. And then now I think it has fair amount, you know, all that I covered plus some things. The main thing is, you know, what it claims is that it does go beyond even loop quantum gravity.
Oh, I think you're.
Can you hear me? Can you hear me?
Okay, you're there's a bit of interference there. Yeah, I can hear you now. Yeah, okay. It's better.
Okay. So let me repeat that. So essentially, you know, I talked about, it's essentially a quantum gravity, but it goes beyond that, my thing. So rank gradation, like I said, very similar to what Emily was saying. You have the lower level and the high levels, you know, the astrophysical and the quantum level. So I see that reflected in the rank level. So in that paper, I have already put how the astrophysical level you can use rank 2, very similar to Schwarzschild matrix. Then when you go up all the way up to quantum level, you have rank 6 tensor, right? Then the mesoscopic level mixed thing. And that's very interesting because you have rank 2 and rank 4. the mesoscopic level.
Okay.
And I was trying to, from the mathematical point of view, I was trying to see how that physics comes, because mesoscopic is what we, normally see. So there should be a simple way to understand that. And I understand now it's a very simple Euclidean thing. If I am, you know, in Arizona, I have the ground floor, right? So when I look at outside, I can see how that rotates with the front and back gaze. But when I come up, I cannot really locate that. And why is that? It's because there's X, Y, Z. You see that? Yeah, I have to move the X axis, then Y axis, then at Z axis, the elevator. I have to go down the elevator. And then I have to rotate right or left, right? So it's a very, I'm just thinking first, but I think it has more deeper things. So which means X, Y, Z, and theta means I need rank 4. And I was thinking that what happens if I reduce it to rank 2, like Rayman thing? I
Yeah.
cannot really see that, because what I see from here is R vector, right? Straight down, it's R vector, which is a combination of X, Y, Z, and R and theta. I cannot locate it. So that's interesting. What I'm saying is that right now I come to the point that, quite simply summarizing it, is that uh, I have to reduce, in order to make it, you know, pencil and paper, I have to reduce the rank, and there's something called matrix factorization. I already show you can convert rank 6 to vector, rank 1 or even scalar. So that is the paper right now. It's called scalarizing time and gravity, because unless you scalarize it, you cannot measure it, right, or observe it. So for observation and measurements, we need scalar quantities. And in that one, interesting thing is that I find Lagrange from there, general Lagrange. And normally people will say, that when you find the Lagrange, everything will, fall out. It becomes just classical, right? That's not
Right.
really true,
Okay.
because I can write Lagrange finally as a function of quantum, the mass, because mass vector, when I scalarize, I get a scalar mass, which is not same as the classical, then a scalar prime, which is not the same as classical. Then I have a space that may be, XYZ plane. But what I did was a problem solving, how I can do it classical. Can I get a classical answer from there? So I took a simple problem of the gravity, going up against the gravity, going up the elevator or something, right? So you have
Right.
very simple Lagrange for that, kinetic energy. We did very similar thing. At one time, we did for harmonic oscillator, we did Lagrange. So I did a
Yeah.
Lagrange for this, and eventually everything has to come to Lagrange. Of course, all the theories come to Lagrange. You know, uh, so I did a Lagrange calculation, simplified, and nicely, I could derive for the classical case. The only difference is that, you know uh, when I do that, I can get equivalence principle. I can prove Einstein's equivalence principle from there. That acceleration is negative of gravity, but I put the gravity. See, the thing you have to understand it is, if you have acceleration here, that's not. This is in the direction of gravity. I solved a very simple z-axis equation, and I started. So when I was thinking, you know, I get a equal to minus g when I derive. How did I get? Oh, then I go back to physics. I instead calculated Lagrange for gravitational situation. Like for example, the kinetic energy is, just half mv square, right? Half mv square, and the potential energy is mgh, whatever, or mgx, mgz in this case, right? So very
Okay.
simple. Okay, so Lagrange is half mv square minus mgx or mgz, and
Right.
then I differentiate the Lagrange to get force, right? So I have to do a partial differential equation, partial of Lagrange with respect to x. Then I get a force. And then I can equate that force, very simple, to acceleration, right? F equal to ma. So very simple. It's all high school physics or just probably freshman physics. Very simple. So I did all that and do the calculus. So fairly simple. Only that's you have to be careful about the partial differential things like that. I will show you sometime. I have send it out, but probably next time I'll show that because I don't have a way. When I go back next week, by the way, I'll be in Arizona, so I can show on a pen and paper. Here I cannot really, so I don't have that camera thing. But
Okay.
next week when Emery is presenting, I will be in Arizona. But
Well, yeah, that's right. Emery will probably, well,
yeah,
he'll do his
she's
thing.
yeah. If there is time, I will show otherwise subsequently, the subsequent week. Because I think the subsequent week is history of physics, the episode 5. So maybe after that. We'll see. Whenever there is time, I will show that. But yeah.
Cool.
By that time, hopefully, they will have peer reviewed my paper. This paper is already having some of it, but the peer reviewed paper, I go more into, the next paper, I go more into that. And I do the calculation. So the classical case, so it reduces. That's important because, you develop the theory and then, but you has to correspond because it's a higher theory, like Emery was saying, but we got to reduce to classical case when you do, the parameters where M is not a function of, distance or time or space or time. So in that case, the differential, everything comes out. It simplifies, right? And V is also, everything becomes simplified, but there's a condition I had to put. So that's interesting part I had to put where, the limit of del or del T goes, L goes to 0, Lagrange. And then that becomes actually, I was thinking the physics of it is that that's of a simple pendulum. So what happens in a simple pendulum? Coming to that, that's an interesting case. So it actually takes care of all that, the math. So in the case of simple pendulum, when you go up, the potential energy is high, right? It is much more than the kinetic energy. When you come down, both of them are supposedly equal, but I find that it's not really that true. So actually, we have to modify that because that's where the vacuum and all comes up. See, the pendulum is slightly above ground, right? So actually, the potential energy is slightly, it's not much, slightly greater than kinetic energy. It's very interesting. So what happens is that the this side is acceleration going up, but this side is gravity. One side is gravity, so it's balancing the gravity and the acceleration. So at that level, the equivalence principle holds good. A equal to minus G, because that's what makes the pendulum. So the interesting case is what is below that. We are going to detail. Like I said, the noise converts, that's ultimate. Noise converts to distorted thing and then signal. And this you can use it here because there is some noise here. So if we keep the idea is that if we keep the pendulum down, right? Just pendulum down for a long time, it will actually start moving because of the noise. The noise will feed that pendulum start moving slightly. And this is something we can test. And how long? I don't know. That's something we have to, that's where your space thing comes into picture. Now, I was thinking about your hyperspace 4-dimensional. How do I incorporate that? In order to incorporate that, I have to use the Levi-Civita thing because the space requires energy, angular momentum, and entropy and all that, right? So we have to use the Levi-Civita conversion of that, and I have to reduce my rank to rank 4, and then use the Levi-Civita. And in that one, there is a rank 4. Okay, that I had to use a Riemann, conversion from Euclidean to Riemann. And the same thing, I think that you have to convert. You have your four for space dimension. Let's say that is X, Y, Z, and U or something. U, V, X, Y, Z or something, right? The four things you need for your four hyperspace. But you have to convert that.
Well,
That's an ingredient.
Is it XYZW or no?
Yeah, XY. Yeah, you can use anything. XYCW. Let's say XYCW.
Okay.
Then you have to convert to Riemann. You are thinking in order to incorporate, in order to connect that with the time that I come in Earth, you have to convert that into Riemann geometry. So the Riemann geometry, what it does, yeah, I showed that briefly in the ICFAX also, and in these papers also, I kind of bring it out. In order to do the Riemann, you have to do an R, like XYZ become R, right? And then you have one more coordinate. So R is the normal real. R equal to square root of x square plus y square plus c square, things like that. Yeah, that's the value of R.
Yeah.
Then you have one more coordinate, R and Z. You can convert to theta if you want to, but essentially you have to convert to Riemann, Riemann geometry with rank 2. Then I convert my Riemann geometry rank 2. Then these two then will commute. Then they will connect with each other. They'll be compatible. So we need to convert everything to Riemann geometry, which people are trying to do. I found that the loop gravity tried to do that, but now the lattice, there is something beyond loop gravity called lattice quantum gravity. And that's where your thing comes in the picture. Why you have these specific things like lattice? It shows like lattice, right? The 5 thing doesn't show up in your thing. You have 6, charge 6, but not 5, right? And that is typical of lattice. In a lattice, you have the group theory, rotation group theory, which I have done in materials, that the 5-fold symmetry does not exist. And we talked about earlier, and some people are contesting that about the 5-fold, but actually the 5-fold doesn't exist. And that shows why the 5 doesn't exist. That's one of the reasons. It may not be, we have to think about that. So that means the lattice is important. The lattice aspect is important. And people are considering that. That's where the lattice, the entropy, especially in entropy, the lattice is very important. So we have the symmetry aspect in terms of lattice. And the 8 by 8, I agree with that. Mine also shows 8 by 8. Very similar. I need 8 by 8. I think I have a separate rationalization why it should be 8 by 8 to include all the charges, mass, and everything. For the particles, we need 8 by 8 matrix. Now, interesting thing is that 8 by 8 is only part of it. Okay, it's only part of it. But when you consider everything, I think we went over that briefly. We will work it out again. But it seems to be working out that you have 24 cell, and then we said that your space thing shows that there should be 4 universes, right? But actually, it will be a lot more than that. With the time, when you consider that, it will be like the power 4 to the power 6 or something. That's the maximum. There's a suprema and this thing. So you have to use those kinds of things. Suprema, maximum number of universes possible. It's not infinite. So the universes are not infinite, but very high number. But there is a smaller number also. So somewhere in between, and there is some rationalization I have come why it is that way. But I am not, that will be further down the drain. I mean, there will be one more publication after this one that I am just sending out. One that is Gallic proof. The next one is now it's going to be reviewed. I just send it out. There may be one more after that because there are a few more things there. After that, our project comes into picture. After that, it's just putting space back. When I put the space back, your 4D hyperspace, everything will come to picture, what we talked about. So that will be just one more paper. After that, everything will be our combined thing, mostly, our project, all the publication, mostly. There may be one more if necessary, but that's it. So that's the way I see it, because I don't want just repeating each one. Every paper should be original. It just should have something new. That's the way I see it. And then once I develop that, automatically when I do that, I going to the most advanced thing, which is like quantum gravity is not enough. Loop quantum gravity, which talks about the space-time as quantized, discrete and space-time. And Emery also is talking about that discontinuum. So I think they are all coming together, but not exactly. Everything is coming together as different pieces of puzzle, but we have to see how they fit together. Not yet. So there are a few more things they have to do in order to fit them together. So time, space, and all that. And why is discontinuum like we talked about with Christopher? The I space things come there because point singularity. Again, I pointed out with the Schwarzschild matrix. I use that. It's not global singularity. It's a point singularity, which means the point cannot be. There's a 0 point, but also there is a point singularity, which is micro black hole. So then I coming out with quantum form and the vacuum bar. So if this is the 0 point, the micro black hole is embedded in there. So what happens is that when they do that, they I have found conceptually that it will first eject the cosmic microwave, and after that, because of black hole, they'll start merging and they'll create a gravitational wave. This you should be able to measure eventually. So I have, I also put some possible experimentation we can use. Now I have not used this one, but for the calculation I had done. So, which means that CMBR, there should be a lag time between CMBR and gravitational wave, and we should be able to go back to the source and then prove that actually it starts with the 0 point and point backward. And then when they merge, it will eject out first CMBR. Okay. And then after that, there's gravitational wave. So if we measure the lag time and, if we put our space and time, all the theory together with this continuum, we should be able to calculate what the lag time is. Okay. It's not same as what general relativity says. It will be different. So the lag time, if you measure that, and if they can prove it with the CMBR and gravitation wave, we have it. We have proved our theory and close to whatever the ultimate thing, the unification aspect. We are just achieving it. But I think it will take at least a year to get to that. Right now, I have put out for the history of physics, and I see, in that one, each episode I go, I know what's going to happen. And then in the episode 8, up to episode 8, I have laid out what it should be done. It's a gradation. The episode 8 contains the lattice quantum gravity. It advances to a level. And at that time, the history of physics lags behind my paper, which is good, because that supplies the information, just literature information, and I can cross-check that later on. So it's a way to cross-check that, and if I have to correct my thing, I can correct it later on. But it is a final state. It is like the final state. So the history of physics moves only. That's why I don't want it to move fast. So after August, it will be in September. Then like that it goes on to completely understand what the literature has come, and it shows only that much of each one, very very specific. And that when we discuss that, we discuss that, you can add, and then I can modify the next one. So we move only such a way that it is a final say that in terms of literature, that we are not putting any speculation or anything like that. That's the way it is. That's the way we understand the physics so far. So like that, if it moves, and I can see based on that, 80% of will be like that. By November or something, I think I will be the 8th episode, and then that will be connecting a loop, quantum gravity, lattice thing, string theory, all this, how people are putting together. So that's what I want to do. And after the 8th episode, it depends on what we are achieved by then with our discussion. And the 9th and 10th will be probably next year, beginning of next year, January or February. And we should be able to finish by then. By March, we should be able to finish all the episodes and then start working for the documentary movie. So based on those things, we have the documentary movie that you suggested. I'll start working in March, April time, and then by summer next year we'll have that, and hopefully we'll have the Luxembourg conference. We'll see how it works. But
oh yeah, I was thinking about the Luxembourg thing. So we looked up the flights, and they weren't too bad, I seem to recall. But
yeah.
I don't know what the cost of living is. Such a bad term.
That's,
you know what I mean?
A good point.
Maybe it's quite expensive there. So
that's
what you save on the flight you might lose on like travel, accommodation, food, etc. Renting of the place if that's needed.
Yeah.
So I was thinking then, Italy, it's generally cheaper, and then there was also another place that came to mind when we were. You brought up Luxembourg last week, I think, but there was another place name that came up at the same time, and I was like, "Oh, that might be a cheaper place." But we'll have to look into all of that, and that's just a cost analysis kind of thing. We don't need to worry about that at the moment. Okay, so
right now,
yeah. Well,
at
the moment here, I'm working on this.
Yeah, go ahead. Yeah.
So
coding, right?
Coordinates. It's a little bit tricky. So I think if you recall, we would have done a lot of work, like what I was saying about going onto the kind of the back burner. Putting the own model on ice for a minute or two, and looking at, maybe looking at some other problems, because there's actually an awful lot of research that needs to be sort of looked at and gone back over. One of them was to do with this set of papers on the isomorphism of the standard model modified and the 24 cell. So there was work done on that where, I was able to get the weak symmetry breaking based on directed graphs and like non-directed graphs, if you like, or tree cycles. And so that worked out well. And then we were also able to get the what's this called again? The color charges. So that would be
the strong theory, right?
Yes. Yeah. The strong force we had. Electromagnetism is obviously in there, the fermions, and all of that. So it was looking pretty good, really, and in a lot of ways, there was a lot of positives. We were able to link it with the quaternions, the general linear matrices of 2, 3, S8 obviously, and S4, and then the coordinates of the 24 cell with the color charges permuted. So that was nice. But then the next phase, which was a much bigger and more ambitious sort of phase, was then to take that isomorphism and create an automorphism of those same particles from the 24 cell to the 600 cell, which is, as you know, dual to the 120 cells. So in this case, we were able to go even further because so the whole idea of these grand theories of everything, grand unified field theories, those things, or even theories of everything, is that you're trying to get all the particles, the anti-particles, left-right spin, color charges, all the bosons and all their interactions effectively, all into one structure. So if you have, like, they tried with the fermions to use SU2, but that's okay. But it doesn't, it's obviously not big enough to accommodate all the particles and
mesons and all, right? Mesons, hadrons.
Well, no, because then like a meson might be a combination of two quarks, let's say, or something, or right?
How about hadrons? Hadrons also. Hadrons.
Yeah, they're bigger. Well,
The
hadron
proton.
is like, yeah, I mean,
Quark.
no, like we're
Quark
talking
shifted.
about it on a more fundamental level, and then you can build everything out of the fundamental level. So, so yes, but so you're not going to be able to fit the bosons maybe in, and as so that was a problem Lisi had with his E8 model. He was trying to fit it all into this 8-dimensional lattice called E8, and there just wasn't. So there was multiple copies of something called SL2C or SU2 in there, and just wasn't able to fit them all in. So I kind of instead I used the 600 cell, and I was able to get all of the particles, the antiparticles, left, right-handed, spin up, spin down, and all the relationships to the weak symmetry breaking through the S8 graphs. And from that, we were also able to generate, you know, well, we have the charge. We take the weak iso spin, and then so we're able to create the hypercharge as well. So, so that makes it equivalent to you know, the Georgi Glashow model of SU5 ground unified theory. So that's quite good. But I think it even goes further. So doesn't seem to mention it there. So we have U1, we have fermion spin, chirality, spin statistics, an analog of SU3 QCD, gluon rotation. That's the strong force. Just don't want to repeat myself too much here because I did get a few of these. And right. Okay, so what we don't, so it goes, and a possibility of an interpretation of gravity with a total of 8 gravitons. But we don't really know what these 8 particles are. We're just speculating 8 gravitons. Alternatively, they could have been 8 dark matter particles. But I think the current thinking is that the dark matter particles are fermions with mass. Yeah, I think so. I've forgotten what the name of that is.
They are rank 6. They're probably a rank 6 noise. Just noise, actually.
I don't know. I wouldn't go. I don't know if I'd just label them noise, but it is interesting. But yeah, so I mean, it, you know, the 8 particles don't even have to be dark matter. They're just 8 unknown particles, and they seem to be bosons. But you know, so basically, that's all we have with gravity in the mix, or dark matter. So we say we could have a graviton as the canonical vertex center of the 600 cell. So the graviton is equidistant, sort of an equal distance from all the particles at any one time. So that's why it affects them all uniformly, kind of concept. So that's interesting. But what we don't have here is, so this is without a doubt, I would say, a grand unified theory. But what it isn't is a TOE, you know, like a theory of everything. And the reason why it isn't that, obviously, is because it doesn't unify all of the
gravity.
Forces. Yes,
all the forces.
Exactly. So that is the next step. And well, the next step on from obviously mapping all the particles to the 600 cell is to then say, well, why don't we increase this now to the 120 cell, which is, as I mentioned, the dual of the 600 cell, and it also has, instead of having 120 vertices, it now has 600 vertices. So it's an increase of 5, right? Here, we're just multiplying all of the particles in the standard model by 5 this time, which is fine because we already have, I believe it is 5 copies of all the particles. I'd have to look into that, but there's for some reason there's a duplicate of 5, but oh no, yeah, right. So when we transport the particles that we had in the 600 cell and transport them into the 120 cell, they'll be copied 5 times. Now that's interesting because you know, in string theory, they got to a point where they had 5 copies of string theory that were all equivalent. And then they used, I think Christian was talking about it last week, how they employed M theory to unify them all. So, but that's not where we're going with this, because we have the graviton, the canonical particle at the center. But if we just put that, say, well, really, if it's at the center of each 24 cell in the 600 cell, then that's 5 copies of the graviton. Then we multiply each of those gravitons by all of the particles in the 600 cell. It's 120, so that's 120 by 5. And that means that all of the particles in the 120 cell are actually, you know, let's say a right-handed electron coupled with a graviton, which is one of 5 copies, or just, yeah. So, and all of them then are coupled with a graviton, no matter what the particle is. They all have a graviton connected to them. And that, so an interesting thing then would be to create this graph, or not this specific graph, but maybe more like this one, of the 120 cell. So to do that, we need all of these coordinates, and use a similar approach to what we did to generate all of the 600 cell coordinates, which is what I'm attempting to do here, obviously. Slowly. It's not, I'm not the sharpest on a Saturday by any stretch of the imagination. Okay, so if we can do that, then we can figure out which particle. Okay, so in order to do that, right, so if the 120 cell is the dual of the 600 cell, like they say it is, then we should be able to, and vice versa, and we should be able to take, like, let's say all the vertices of this dodecahedron here, get its average, get their average, and that will give us a point at the center, which will be equivalent to a vertex in the 600 cell. And then we can do the same thing with the 600 cell and get back all of these points. So then we will know which particle of the 600 cell corresponds to which vertex in the 120 cell, which is important. And then we need to, isolate them. Say, okay, this graviton is associated with the left-handed electron, let's say, in this group, in this cell. And then this one, the graviton here is associated with an up quark, and the graviton here is associated with a gluon, and so on and so forth, until we have, just a general idea of what the particles might be. So that's going to be a little bit tricky because there's some disorder probably in our lists, but maybe not. We'll have to cross that road when we come to it. Let's see if the lists are disordered or not. So there's lots of things to be worked out. Then, so what I'm saying is we've already unified a lot of stuff with the 600 cell, and as I mentioned, I think I mentioned this previously, that the aim then is to unify everything finally with gravity using the 120 cell. So that will be a theory of everything. But before we can get there, we need to solve some basic problems. So in this frame of reference, its 600 vertex coordinates are the permutations and even permutations of the following. So what do they mean by permutations and even permutations? Because Because you know, if you have permutations, surely the even permutations will be contained within the permutations, right? Because this is all permutations.
Yeah, that's a bigger set. Yeah, that's a bigger set.
Yeah.
Permutation will be a bigger set.
So are they saying all permutations plus even permutations, meaning we want to add the even permutations to the set? So we have twice these, which sounds a bit odd, doesn't it? Because then that's just the same. They'll just be the same coordinates twice, I think. So this is the kind of frustrating thing that you run into using.
It could be is there a prime number involved in that prime type of thing? I don't know.
Not specifically. Oh well, there's no, not really. It's mostly the golden ratio, which I don't think you describe as one, but obviously there's the number 5, right? Square root of number 5. Yeah.
Golden ratio. Okay.
Golden ratios is an important aspect of this, as it is in the 600 cell. You know. Okay, but so that's one issue. But then we also have the second problem. You know, when we look at the 24 cell, it's often referred to as being self-dual. So it sounds like what they're talking about there is that we want to take all the coordinates of the tetrahedrons, let's say, or yeah, in the 24 cell, find their average, and then we'll get the coordinates for the dual 24 cell. But in fact, that doesn't work, because what they mean by self-dual is that when you rotate by, let's say, 180 or pi rotations maybe in the fourth dimension, you just get back the same shape. So
invariance, right?
Right. So it's not the same thing as dual in terms of geometry. It's some other group theory it's self-dual rather than just dual. So I'm thinking that when they refer to dual here, they actually mean dual. So that will be something that we'll have to do. And in order to do that, we first need to generate all of the coordinates. Now, I haven't looked at this in a while, so it's going to take probably some time before this, you know, before I can get it definitely won't be done today is what I'm trying to get across. Now, on that front, there was some research I did last night, which I should probably share. And the subject of the research was to do with there's this thing where you have SU2 or was it GL2, 3? That's not coming up, so it's a bit concerning. Did I forget to save it? It's a lot of work. Well, it wasn't Ahmed, but you know, no, actually, it was a lot of work. Looks like I may have forgotten to save that, which isn't very helpful. But I suppose it was null. It was null results anyway. GL23 was like null. Oh, there it is. So, okay, it is in there. Particle interactions, GL23.
Is it color charges? Color charges you consider?
No, not this time, because the color charges kind of worked. Well, actually, no. Yeah, you're right. It's everything. You know, it's all the different forces and all that. Okay, so we're going to hit name here because we know where we're where we're searching. Okay, so I know what it is. Is it iCloud? Then class modified. There we go. It's in a different container. Now, okay, so we import NumPy, and then we have all of our quaternions here, just arranged as vectors or coordinate vectors, as a list of strings. And then we have a dictionary which says which of the GL23 matrices correspond with the quaternions, sorry. And then we can build GL23 out of that. So that's all 48 matrices. Oh, I changed the name, did I? Okay, not to worry. So if I change that to G, that's this is typical, isn't it? Worked the last day. I might have, anyway, it doesn't matter. Here they are again, because, and then that's matrices. So 40 and 48 look very similar, actually. I hope I'm not, there we go, 48. Now, so then, right, well, we need to duplicate some of them because we have all of the leptons and all of the quarks. So they're going to be the same group, but they're going to be duplicated. So then we take fermions, and then we zip them with all of our matrices, and there we go. So now we have, let's say, the right-handed anti-tau, and the right-handed anti-tau neutrino, and the muon, the left-handed muon, and these are the associated matrices with those particles. Now, the next thing to do, so I think I mentioned a while ago that the whole theory about using these SL2C particles or whatever, because SU2 and SL2C, if you like, well, these aren't complexified, so you know it's I think it's SU2, or is SU2 imaginary, or anyway, it doesn't matter. These are the real matrices of like SL2Z or something. So
it's more like a poly, right? Poly. Right,
poly would be imaginary, right? So that's SU2.
Yeah.
And then SL2Z, because Z are the counting numbers. So this is SL2Z mod 3, I think. Anyway, because, right. So, okay, so what we're trying to get here is that when we have that group, that's non-commutative. Well, some of them are, right? So if we take the dot product of one matrix with itself and then the inverse version of that, do they commute?
Yeah.
Are they the same matrix? And if the result is the same, then supposedly, so let's say if we were to multiply G8, the 8 gluon here with this G8, if they come out as the same, no matter which order we do that dot product in, then we say they commute. But if they aren't the same, then they don't. Well, we know they don't commute, but they don't interact, is my point. So they don't commute, they don't interact. They do commute, they interact. So that, I figured, was a big test then for, let's say, all of this model, you know? Because if this model is predicated on SL2Z, and I think I was saying SL2C in this document, but that's obviously wrong because it's not complexified. So that was my mistake. So we think, right, if it's SL2Z, then, and we're using these matrices, and the whole point of using the matrices, aside from something like Clifford algebra, which we also looked at in a previous tags thing, and I showed that you can't use this group to generate spins, for example, in Clifford algebra, which is the claim made by a lot of mathematicians and physicists, or physicist mathematicians. I tried it, it doesn't work. there's only like one or two matrices that give the right answers, and the rest of them don't. So there must be a step I'm missing. Like you could convert the matrices into the correct ones and then just use those. Okay, fine. That seems reasonable. But this concept, it seems like a fair test of this theory, or maybe a fair test of the mathematician physicist's theories, would be if we were able to get the particles to commute or anti-commute, and therefore interact or not interact based on SL2Z matrices. So, you know, for example, the photon is going to interact with the electron, you know, whether it's right or left, it doesn't matter, or, you know, anti or positive, or
yeah, they could produce positrons, right?
Yeah, or a positron. So all of those things are going to interact through the magnetic thing, right? And
magnetic,
then, and then the electron is going to interact with the weak force, and the weak force is going to interact with the neutrinos, and so the neutrinos and the electrons kind of interact. So basically, that's what this code here does. It asks, or that's what this code does. It asks, are these equal? And then it prints them. So we see that a tau right-handed interacting with or an anti-tau right hand with another right-handed anti-tau, they do interact. That seems fair, right? But
it depends on energy level, of course. Energies,
Yeah, just in general, right? You know, if they come into contact with each other, there's going to be some sort
whether it can or not. Whether it can or not.
Each other through the electric force. So they're both positive. They're both charged negatively in this case. So they should repel, but then they both have the same spin. So I don't know. Okay.
Yeah, that's complicated.
Yeah.
Yeah, it's not simple when you go in there.
Might override the spin. I'm not sure, but we can see here that a tau electron with a neutrino tau, they should interact, but they don't. And in fact, what we see is that there's an awful lot more in these groups, because this is all anti-tau right-handed to begin with, up against all of the fermions and the bosons, with some of the these G7, which are kind of gravitons, unknown particles in the mix. And basically, so we can run down now, we move on to tau neutrino, and then the mu, the left-handed muon. I keep calling it a mu, sorry.
A lot more not interacting than interacting.
Yes, exactly. So, and that's kind of obvious, isn't it? Because if we think of if we think of a grid, like a matrix, and we have the, you know, like in the tensors where we have time and then the three spatial dimensions, it's only along the diagonal that we get the metric, right? -1, 1, 1, 1, or the other way around. So because it is only on the diagonal that we are going to have them commute. At every other point, pretty much, we would expect them to anti-commute, or to be just non-commutative.
Symmetry,
To
the diagonal, they satisfy the symmetry.
Diagonal. Okay, so that seems to be a fair assumption, and you know, so I think that's a fair assumption. So we can straight away like rule out the idea of using maybe GL23 or copies of SL2Z and saying, you know, applying them to all the particles in the standard model, and then asking, can we use this to say, do they commute or not? Because there just simply isn't enough possible interactions between them to allow for all of the types of interactions that we'd expect to see. So I would say that obviously if they're using that, they must be using it on a much smaller subset of particles that are maybe handpicked to follow certain rules.
Mm-hmm.
But what we cannot use it for is anything in this. So I'm going to drop that. Initially, I was using it, okay, but this will prove or deny the theory. But now I'm just thinking, well, why would it prove it? It just doesn't have the capability to prove it, right? Unless we say that, unless we were to flip it and say when it doesn't commute, that's when it interacts. But even so, it's too restrictive because we're always going to get the same number of interactions and the same number of non-interactions. And I don't think that the standard model is that clean. It's much messier. So, yeah. So I'm just going to ignore that. You know, I'm trying to build on the work of previous physicists and mathematicians. And in order to do that, I need to know what they're talking about. And as you know, and as I know, and as everyone who listens to this knows, it's very difficult to understand what they're talking about in general because they rarely explain it unless they're explaining it to people who just don't know anything. And if they do explain it to people who do know things, they're explaining it at such a high level that it leaves most of us behind. Certainly in like papers and stuff, it's going to be a lot of equations. You know, you need to be like postgraduate, you know, in a specific type of mathematics to even understand.
I was going through yesterday some of the literature in loop quantum gravity, lattice quantum gravity, more advanced than the quantum gravity itself is advanced. But the next level I am going through. And the problem is that, you know, there are a few authors who are doing very good job of explaining, but most of the symbols they don't explain. Most of the abbreviations, they don't really say what it is. They keep using it. And I'm not sure whether they are correct. You know, they may be misinterpreting some of the things. And the symbols also, they say covariant, variant. You know, I would think that what, you know, the tangent space and the covariant talks about perpendicular tangent spacing. But they, you know, there's a simple way of explaining that they're wrong. And that is getting messier. And finally, they say, okay, SU2, SU3 doesn't work, SU. Why? They don't really, you know, rationalize why it is so. They don't give correct reasons, I think. And that's part of the problem, you know. I mean, there are a lot of maths, I agree that, but so complicated that they have to simplify it. They have to break it down. That's what I'm trying to do. The more the math I do, eventually I can simplify it to very simple things that I want to calculate a Lagrange and say, okay, when you reduce it to the classical case, it applies. And they have to show that when you reduce it, it applies to a classical case. I'm sure that will be one gauging important factor because you can reduce the, you know, all that quantum mechanics or relativity says that the classical cannot explain that because the things are varying. But when you have the same thing occurring, it should reduce the classical case, the Newtonian or that. That's a very important test, you know.
Okay. Yeah.
I think they don't really show that. Yeah.
That seems about right. You know, what you're saying there sounds legit. So I'm interested, you know, I think that's kind of it. I mean, you know, I think I mentioned everything that, you know, all the research that I've been doing and up to now, you know.
Very good job, Christopher. I think you are going the right direction of being thorough, Christopher. I think I like it because I think these have some validity, you know, useful. We'll come up when we do the project together after I finish the, you know, sometime few months we should be able to get on to that and then use these things. I think when you combine with the time and the Riemann geometry, I think we will get more understanding of the physics.
Well, this is it, Rajan. You know, we were just talking about complexity and you know, the difficulty of notations and stuff. And I understand that Riemann geometry is used, like, for example, in general relativity, but
not that much. See, the thing is that Einstein make into Ricci tensor. He uses pseudo-Riemannian, right? But now they're saying that when when I read about the loop gravity and lattice quantum gravity, they said we have to go back to a Riemann. And I agree with that aspect. Yes, we have to go back, not just pseudo-Riemannian, but Riemannian itself, we have to go, because...
Well, the point I'm trying to make here, and maybe I can make it in a kind of elliptical way that, that will make it a bit more clear or something, is that, okay, so here I am trying to figure out the coordinates for the 120 cell. Now, that's okay, and I'm using Cartesian coordinates, I believe. That's what these are. So if we look at, and the whole thing is that we're going to take this this 4-dimensional lattice, it's not a lattice, polytope. And well, it is a lattice of a kind. And then, right, so then we're going to transform it in a certain way into a lattice, actually a cubed lattice, and then we're going to transform it again into a hyperbolic space. Okay, and the reason why we do that is because 4-dimensional polytope with 4 spatial dimensions isn't going to play well, or play nicely with general relativity, which is 3 dimensions and 1 of time. So, but the 3 dimensions and 1 of time, as we know, leads to such things as like hyperbolic geometry, because we're talking about hyperbolic curvatures, and then in the Lorentz transforms, we have, as we saw before with the Lorentz lattices, we have hyperbolic transformations. So this is going to lead us into a hyperbolic net of a dodecahedral kind of lattice, which leads to hyperbolic knot theory. So I was looking into this work by this woman, Purcell, still related to Maslow and Marsden's work, all about twists, knots, and link complements. Okay, so it's all very interesting, but what they do is straight off the bat, they call the knot K or something, and it exists in S3, and then they go, instead of like sitting in just normal Cartesian space, they say, okay, now let's go to the they call it the knot. It's also like
kind of like string theory, right? Kind of off string theory type of thing.
Yeah, I think this is very heavy math stuff, really.
Yeah.
And then string theory, there's a connection there to well, the way I was talking about the 5 different types of string theory.
Yeah.
And then they get to, like, there would be a connection, obviously, because you have certain types of knots which are just looped around a torus, for example. But yeah, so, and obviously that's a big thing in string theory. But and then I think they're probably connected in a higher way through certain other types of what do you call those things? Like the Langlands program, where they're trying to mix group theory together with matrices and blah blah blah. And so there, they found some connection between, what were they called? Not p-adic numbers, but like gamma matrices or something like that. And they, but not the, or it's like, anyway, I have to look it up. But so they found something, and they said, oh well, we can connect the E8 string theory to the, what was the names of the 5 string theories again? Heterotic
superstring. There's brane also. There's a brane.
No. I'm talking about within string theory. You had 5 different string theories. There's like heterotic E8 string theory, and then there's the one where they just connect on the. Anyway, so there's 5.
Swampland. There's a swampland, but it's not.
Well, I'm not getting into that because that is literally a swampland. But Yeah. So the thing. Okay. So one string theory connects to another through this higher order maths, but and so you can connect those two, and then maybe one of those connects to another one, which connects to another two. So it's not like they're all unified; they're all connect to each other, and they all become this. It's like this one connects to this one with one method, and then using a slightly different method, we can connect this one to this one, and like the actual connections are pretty tenuous, but like it's kind of cool, but it's definitely not rigorous. And people, I think Witten was either the main guy or one of the main guys who noticed this first, and he even admits like, oh, you know, the connection to this higher math stuff is like tenuous, like it's there. It's
landscape like, is too vague. The landscape is too vague, whatever you call it.
Yeah. So it's you know, they did it anyway, but it's really like, I think like, given how, you know, fantastic they are at physics and that,
a lot of hand waving arguments, you know.
Of course. well, yeah, but so considering, you know, they're on a different level than I am, but you know, when you're working and then you get to the raggy end of your understanding of what's going on, and you're like, bit of hand waving, and then ta-da, you know. So I think that's what they were like. We're at the limit of what we can do here, but still we're confident enough to say that this is correct. And so, and then they can probably do other stuff.
They force fit, something called force fitting. They do like mixing of the dimensions and force fitting the units, that type of thing, you know. So
okay, yeah, that could be another method. Yeah, it sounds interesting. That's more of a kind of a trial and error or brute force kind of method.
Yeah.
So
exactly.
Yeah. So I don't even think they you know, brute force, fine if it works. Usually, I don't even think they have that kind of level of certainty, you know. So, but certainly, brute force computational kind of, you wouldn't have like a closed form solution or even necessarily a mathematical equation to back you up.
There's a numerical general relativity. You know that, right? The people are now developing numerical general relativity because there is a memory effect. I mean, that's an interesting thing. One in Caltech, I think one guy in Caltech is doing that, or someplace. He's proven that there should be a memory effect. And if they find that, of course, you know, that's correct. From numerical relativity, so there should be a memory effect because of the way the things are. I think it may be partly because of the Christopher symbol and all that, I think. But whatever it is, the memory effect is an important thing. So he explains a lot of things on the basis of that. If they find experimental proof, well and good. I mean, it's an interesting thing.
What is it? Is it like it's space as a memory or something? It's like memory foam. If a planet was in one place at a previous stage, the space knows how to bend better or something. I don't.
Yeah, that's memory effect. Could
ridiculous.
Could affect
Star Trek or something where eventually, like, space could get worn out in a certain area because people have been planet's been sitting there too long. But anyway, the point I'm trying to get at here is that you know, they wind up complexifying things and just using the upper half plane of like the complex and some sort of Riemannian geometry, and it's like, oh, did you really have to go there? You know, you just sort of you know, you could have stuck in some other area. Well, that's what I'm thinking. That's what I'm hoping, that I can do this without going into any complicated.
Occam's razor, you know. You have to use Occam's razor. Yeah, that's the key thing.
And then also, a lot of that NOS theory stuff is very specific to that area of mathematics that we were talking about. So what we're so the whole thing here. So we're not going to be following them because they're using like a lot of and physicists have tried to use this before as well to describe
only what we need.
The shape of the universe. Yeah, exactly. So what they do is they take this fundamental domain and they copy it around the place. So actually, each of the cells in this hyperbolic tiled model are all the same. So anything that's in one cell is automatically copied into all the others. And so, you know, they say light curves around it, but it's we won't be doing that. We'll have all the cells are different, and I suppose I should, you know, maybe make a presentation about this subject later on.
Yeah.
Because rather than discussing it here, but what we could attempt to do is to generate the rest of these coordinates. But how long have we been going for, Rajan?
It's about hour and 45 minutes, close to.
Okay, so that's quite a long time, actually.
Yeah.
So
well, you can, whenever you.
So what do you want to do? Do you want to? Oh shit.
Yeah. So interesting. I just want to. I was thinking about the Schrodinger from fundamental point of view. Schrodinger, how he came up with an Einstein came up with. I found Einstein. I think I may have described in some other way. I described, but the Schrodinger thing. Remember, I did a paper you may have seen about a fixed law of diffusion, right? So around that time, that was a big thing. It explained a lot of things about physical chemistry and all diffusion, because it cannot, the concentration cannot sit in one place. It has to diffuse, right? It's a very important thing. So I would think, I don't know whether it's correct. I was thinking how Schrodinger came is that he was looking at the sky, and the cloud, right? So he said that the cloud doesn't, even though there's you can think of like concentration gradient in a higher level, right? It doesn't immediately come to the ground. So he said that there should be a potential energy that is keeping it up there. He said, if I add that potential energy to the fixed in, maybe I can get something out of that. And lo and behold, I showed in one other paper, right? That's exactly the connection between quantum mechanics and the continuum, right? So he came up with the idea that there has to be a discontinuum because it doesn't it stays there. So the potential energy makes it not continuous. It becomes discrete. Now Penrose tiling and all. For example, Penrose doesn't believe much in quantum mechanics. He's refuting it, right? He's saying that multiverse is a many worlds theory, eventually quantum mechanics, but it's not correct now. But when he's doing tunneling, he's thinking, in his mind, how to connect, like with tiling, you have a building, when I look at that, and you connect all the way up to the cloud, right? So the cloud should immediately collapse, right? Cloud should connect to that continuum. So that's the idea of tiling. I was thinking, what makes them think that way, about tiling? That makes sense to me. So you develop this tiling, and then of course you have to do the math. So it's complex math. Then you come up with the different universes, things like that, naturally. So he said that then you interpret that in terms of general relativity. That's what he is doing. He believes more, I think Penrose believes more in general relativity than he doesn't really believe in quantum mechanics, I think, per se. Whereas Higgs is the other way around, right? He's all about quantum mechanics, and he eventually want to prove the standard model, and his thing was quite made the standard model meaningful, verifiable, kind of, with the Higgs mechanism. But in any case, so these two people are two different worlds, right? So people are trying to tie them together, and I see that you have a real problem. General relativity here and quantum mechanics here. And I was thinking about general relativity, if I can remember that, what I was thinking, again, that was very deep thought I had, if I can remember because then I saw the connection. That's why I eventually came to Riemann manifold, things like that. because I don't like to go into complex things unless you need to, keep it
Yeah.
as simple as possible. But I find that simple things, like I always have difficulty finding a direction. When I go, oh, it should be, oh, if I see that I have to go this way, right? Normally it's wrong. I have to take a left turn instead of right turn.
Yeah.
So I said there should be a math way to explain that. There's a math involved that. Now I know it's the rank of the thing will explain that what rank we are talking about. So that's why mesoscopic,
Okay,
it
what's
can be
giving you
ranked
that
to,
impression now? How can you say that?
huh?
What
Because what's
where's your
happening is
justification?
essentially, I mentioned this, right? What happens is we can use the reduced thing, like R is square root of x square plus y square plus z square, but you cannot use them all the time. Sometimes they are separate, they are different. You have to, it's like polarization, kind of like polarized geometry, you can say that sometimes, and that's true in quantum mechanics, that the directions are not, you cannot combine them together to produce a vector, what you call a equivalent vector or resolved vector. It's not always possible. That's why the Euclidean geometry doesn't work. The Euclidean geometry works all the way. You should be able to always find the hypotenuse or whatever, the equivalent vector, the effective vector called R, which is the real, which is x squared plus y squared plus z squared. It should commute with each other, right? They should be, but it doesn't happen all the time. Even in mesoscopic level, sometimes you have to see them as separating x coordinate, y coordinate, z coordinate. So then you have to use the rank, because they move in a certain, they have specific direction, they move in a certain way, and they are sequential things. Only when you do X, you can do Y. Then only when you do Y, you can do Z. And you cannot do the other way. So they don't have commutation. They don't commute in the sense that, what you call, you cannot use the reverse way. I cannot do Z first, Y then. If this R vector is true, the order shouldn't matter. I can do Z first, Y, and then X, right? The order shouldn't matter. But actually, a lot of times the order matters. The order matters. I cannot use R. R
Well,
means I can use either way.
order matters
I don't have to worry about order.
for what? Because we just looked at that in terms of quantum mechanics, with the SL2Z,
Yeah.
and we said order matters, and then we tried it out, and it didn't matter, or rather, it just gave the wrong results. So, are you talking about quantum mechanics, or are you talking about general relativity or something? Order would matter in terms of
polarization.
Well, when you have two matrices or two tensors, and you're multiplying one by the other, or something like that, or you're saying the particle or the spaceship took this trip, and then we say, well, it went, this matrix times this matrix, but that would be different than if you said that matrix times this matrix or something.
Yeah.
Well, but they're kind of equivalent, are they? Yeah, so that's true of matrix things. I mean, that would be true if you're talking about Cartesian, or if you're talking about Riemannian, because if it's non-commutative, it's just non-commutative. It's going to be non-commutative everywhere.
Yeah, that's true.
It doesn't matter if you're using Riemannian or if you're using Euclidean.
Yeah.
It doesn't matter.
But you can use a general coordinate. See, the good thing about Riemann, you don't have to use Cartesian. You can use a general coordinate. It could be in any direction or anything.
It just depends on what you want to use, because, like you say, because it's more convenient or whatever. But there's no strict reason why spherical coordinates are like the easiest thing. I think when it comes to space-time curvature of a planet or something, excuse me, I think that in that particular situation, it would probably be pretty useful. Where's the search on this? Is it?
See, one of the things is that for example, quantum mechanics, like particles. Let's talk about particles. The
Well,
particles,
wait a second. I just want to talk about it. So you can see how like
okay.
spherical coordinates would be useful here. And then let's look at the equation. Is this it? I want the full equation so we can. So the thing I'm curious about with this equation.
Yeah.
Well, this is just the Einstein kind of Hilbert field equation.
Yeah.
You know how like you have the satellite here, and then it's being drawn to the Earth. Let's say the satellite has zero. It's moving at 0 kilometers per hour, right? And it's just going to be attracted to the Earth. Yeah, it's going to impact. Wherever. But if it's rotating, it's it'll go around and then it might impact here. But if it's rotating fast enough, then it's just going to be in a stable orbit, right? Yeah. And then if it goes too fast, it's going to reach escape velocity. It's going to fly off into space. Yeah. Okay, that's fantastic. But if we think of Newton's gravitational, all the Newton's theory, then we have like this law of attraction. So presumably we have a force which kind of talks about kilometers per second. So we're talking about how fast is this going to move towards this and vice versa. I'm just thinking, where is that in this field equation? At what point does it come out as? Is it here? That's the gravitational constant.
What it says is that, like Wheeler said, the mass curves the space-time. The space-time tells the mass how to move. You see that? So there's a sequence.
Yeah, that was that was something I was thinking about, right? So it's saying matter tells space how to curve, and curved space-time tells matter how to move.
Yeah.
Okay, so let's look at this again. If we, so here we have the matter curving space, and then the space telling the matter of this how to move. And then this also has a gravitational field, however small. And so that's curved, this is curved. And then, so we know that there's like
two curvatures. Different curvatures.
Two curvatures, and then we sum them together. And then the kind of the deepest part of that curvature is where that's the route the satellite's going to take through like three-dimensional space. And obviously there'll be a four-dimensional component of time, but that's not really that important. Although I would like maybe to get back to that, but okay, so so matter is telling space how to curve, but then I don't know if it's telling it. It might be telling it how to move, right? But it's not telling it. It's not giving the initial conditions like we just spoke of what is the motion of the satellite. Because if the satellite is completely stationary, then I agree. The equation is going to say it's going to move along the deepest part of the channel until it hits whatever it's being attracted to. But if it's already in motion, then the curvature is not, if it's in like a stable orbit motion, the curvature is going to put it in a circular orbit. But so
you have a saddle point. You have a saddle point.
On the motion that the object has already, how the curved space is going to tell the object how to move, right? So where is that in this equation? And then ultimately, where is the? I'm sure it's in there. Maybe it's probably in the
You have the stress tensor. You have that stress tensor T mu nu, right?
Yeah.
That talks about the matter. Okay.
Yeah. That's the energy
and
density.
Then you have the Ricci curvature. That's going to tell about the equation of motion in the ds square. ds square equal to
Okay. Very interesting, isn't it? So
short-side metric. You have ds square equal to the space-time equation. ds square equal to c square, d square, dt square, and all that. That tells about the equation of motion. So the Ricci tensor is going to tell the equation of motion. whereas steam, going to tell how the matter is going to cover the space time. It's kind of simple. I mean, I'm putting in a simple way. It's a
Right,
little
but
more complex than
I
that.
just don't see it here, like where we have this or sorry.
Yeah, people are not explained it very clearly, that aspect.
Yeah,
but
yeah.
I think that's
okay. So
that is the
it's
thing.
in there. So I mean, I was thinking about one of the big problems with general relativity. They say is that it cannot be modeled like like on a computer. You can't
Uh-huh.
you can't actually
That's
model
what
it.
people are trying to do. They are made into numerical relativity, where they are what you call they have numerical method is basically discretizing it, right? Like instead of the calculus del d by dt, you would say del by dt. You make into finite elements or something like that, small elements,
Is this it
and
here?
then
Numerical relativity.
yeah.
Okay, so yeah, so this is it. I'm interested in, well, sort of interested in doing this.
Yeah, it's an interesting area.
Yes.
I
So
just barely started touch about it. I came across this and I found it quite interesting for computational aspect.
okay, so I'm just wondering though. I'm not seeing any
You have to
like.
put in the YouTube. Put a YouTube and then numerical relativity. You might YouTube. You put a YouTube after numerical. Just put a YouTube.
Yeah, and what am I going to get when I do that?
There's a guy who gives a very nice thing. I can pull up. Let me see whether I can.
Well, no, I'm going to do that. But the point I'm making is that if I look
How
at
to do it?
like the Wikipedia page here,
Uh,
I'm not seeing any of the, what I was talking about, using a computer to like, let's say, graphically simulate.
he go down. It says computational something. Go a little
I
down a
know, but
little bit.
I'm not seeing they don't have any. They have computational methodologies. I'm just, they just didn't make any cool graphs showing the
No,
method.
you put along with you put another thing, computational. After numerical generality, put computational methods or
Oh,
something. You
here's a simulation of binary
yeah, this
star.
guy, I think.
Okay, cool. Okay.
Simulation,
Cool.
yeah.
Yeah, here we go. This is what I'm talking about.
Yeah, okay.
This is the kind of thing. So, yeah, I'm thinking we could try something like this as well, another stage, but it won't be anything quite as complicated as this. I think what's the word? Using supercomputers and stuff, and
yeah,
this is very detailed. I'd be just looking at a very simple kind of model. Still, be interesting. Oh, look at
in
that.
general, what's happening is that it has certain curvature, small curvature, the satellite, and Earth has a larger curvature, and these curvatures interact to produce some welts and things like that. They produce locally, saddle points, local maxima, local minima, and things like that.
Yeah. I think I got you there. Okay, so Rajan, we might take a break, or do you want to
Want to take a break? What time? Let me see. We can continue next week, but if you want, you can. Either way, it's fine for me. If you want to take break, that's fine. Or we can end it here today.
Yeah. I think we did a lot anyway. So
yeah, 2 hours. We did 2 hours.
Yeah, that's good enough
yeah,
time.
that's pretty good.
Okay, so we'll end it there, and then next week we'll have Emery doing hopefully. If he's still on track for doing that, then we'll have Emery doing modern day Grail Quest, which should be interesting, pretty exciting.
Yeah.
Okay, see you then.
Yeah, sounds good.